Okay, so we're talking about areas of infinite or better yet unbounded regions. So that's another way to not to confuse two words applied to two different things. So infinite quantity, that's one thing, and that's what we have discovered. A certain quantity turns out to be infinite, as we have seen it before. But the region is the region as a geometric quantity, a geometric entity is really is it infinite. You can say that it is unbounded. Everything we have seen previously in terms of integrals were bounded, and so this one is just the region is unbounded, but the area is bounded. Okay, so that's the major computation. So whenever we talk about improper integrals, that's the examples to start with. We demonstrated that the yellow area, the two yellow areas, as a matter of fact. We did the right one, right bottom, and it turns out to be infinite. As always in calculus, you may have noticed that every time we see infinite or potentially something might be infinite, how do we handle them? There's only one way to do it, and that's limits. Okay, so we understood that unbounded region, its area of the unbounded region, in terms of their areas of bounded regions, the one on the left, and then took the limit. Okay, so that's the idea. The unfortunate, if you see it unfortunate, the result was infinite, so that region is not only infinite in length, but it's also infinite in area. Okay, that's what the yellow one tells us. Before we proceed, we'll look back why we cared about it, or at least one of the reasons why we did was to look at this picture. Okay, so which kind of hides the problem in the middle, and then you attempted to integrate between negative 1 and 1 by the fundamental theorem, and end up with 0, while in reality is both of these areas are infinite. The area, green area, on the left and on the right is infinite. So in other words, it's not logarithm 1 minus logarithm 1 equal to 0, but rather it is, in fact, infinity minus infinity. What's the meaning of infinity minus infinity?
0.
No.
Indeterminate.
Yeah, I would. That's one of the answers. Yes, it is. If nothing, you see nothing but infinity minus infinity. The answer is indeterminate. Then, if you actually see more, then you go backwards and investigate where it came from. And usually, there is some limit behind it. Behind every infinity is a limit to infinity, and indeed we will realize that these two regions, those two integrals, those two areas, represented by certain integrals. Those integrals are limits, and those limits are, and that's how we got to limits. And in that sense, it might be meaningful depending on the circumstances. It might be 0. It might be infinity. That's the problem, is when you have an expression that could be different things. That's what makes it indeterminate. Okay, but if you specifically identify what those limits are, then you might make sense of it. So, for example, limit n squared minus n, or n goes to infinity. So if you just look at it as two limits, where does n squared goes to infinity. Where does n goes, it goes to infinity. You subtract, what's the meaning? We don't know. But if you look at, you have them as one limit, then what is the limit? Limit of n squared minus n. Limit n squared minus n is what? Well, we will. I guess what's the confusing part is that these are integers, and we haven't talked about limits of sequences yet, but think about of these as x's. X and x and x. So what is it? It's a function which happens to be a quadratic polynomial, x goes to infinity, where does the whole thing go? Infinity. Right, so this is actually infinite. So infinity minus infinity could be infinity. That's an example, or it could be any number. Or it could be zero. So you have to work it out if you could. But if you see nothing but this, the only way to describe it is indeterminate. However, infinity plus infinity, what? It is infinity. So sometimes you could do some algebra with infinities, but not all. So subtracting is indeterminate, but adding is okay. It's infinity. Okay. So there is a little bit of algebra that a fairly short list of rules that you can or cannot do with infinite limits. Okay. So that's the basic example. Then we went on to look into limits into other functions that have strips narrowing down even faster, 1 over x squared going faster, and the result was the number was finite. Okay, so you cannot tell ahead of time what is going to be. So it's narrowing down. That makes it possible that the limit exists. The area is bounded. But it doesn't have to be this case, this way. So we don't know. You have to actually carry out computations. And since you cannot even approximate it because it goes to infinity on and on, so the only way to do it like this and actually compute the actual integral over b, okay, and then take its limit. Okay, so reciprocal of powers give you infinity with if power is 1 or less. And if it is larger than 1, it always gives you a number. Okay, so and then the final example is the exponential function that gives you a number because it's decreasing faster than any other. Okay, so then we gotta now put this together into a definition. So let's recall first that integral from a to b f(x) dx is defined as the limit of Riemann sums. Okay, so we're not going to go into that. We don't have to, but it is crucial that the limit is over. The integral is over closed bounded interval. That's what AB is, and then there are a bunch of others. What other intervals do you know? Closed bounded, what else? Unbounded, which is what? What? An example, what?
Negative infinity to infinity.
Negative infinity to infinity, that's one. Okay. Any others? Unbounded? Half of it. Yeah, negative infinity is 0, as well as 0 infinity. Once again, you could include 0 or not. So, but these will be our first interest because that's what we just saw, right? We saw it roughly. This is what we just saw, right? The integration over an interval which happens to be infinite on the right. Okay, so we actually did from 1 to infinity, but it's just as well. So that's what we have 1 from infinity 1 over x dx. So integral over 1 infinity. 1 infinity. So 1 in including, why do we include point or not include? Infinity we don't include because infinity is not a number to begin with. So we cannot include it. There is no value of the function at infinity. Okay, but we do include, and that's why I don't want to include 0 because 1 over x is undefined at 0. But if you start with 1, you're fine. So every point from 1 to infinity, every single number is where the function is okay. It is defined to begin with. It is continuous also, and in fact, if you keep the limits bounded, not going all the way to infinity, then the function is integrable. So the integral is defined, and that's how we were able to figure out what this limit is. Then you certainly can carry out the same plan, same computation on the left. So you could also look at negative infinity, say -1 on x dx. Pretty much identical idea, so it will be, this is what we're talking about. Okay, and then these are the two infinite intervals that we did not understand up until now, because as I said, this is calculus 1 approach, the initial introduction of the definite interval as a limit of Riemann sums. For the Riemann sums, the interval has to be closed and bounded. Okay, so now we look at all of the other possibilities, and for the most part, we look at well, these unbounded to begin with, but there are also, even though it is bounded, but what? So these are unbounded, they are closed. And then the second class that we did not cover, so unbounded, we started with closed bounded, now we have one class, unbounded, closed but unbounded, and the second one is bounded but not closed. Can you think of one? Bounded, not closed? Well, what makes interval AB closed? The interval we started with.
That you're including A and B in it?
That's right. So AB included. That's what makes it closed. So included. So that's what makes it closed. So if it's not closed, it means that either one or both are not included. So examples would be AB, AB, and the other one, AB. So brackets indicates it is included. Parentheses indicates that it's not. So this one is, by the way, is called open, and the other two are called half open. So our interest will be, for the most part, the other two. So that the idea is that just to deal one bad point at a time. So remember, it has to be bounded, closed, and bounded. So we can only deal with one problem at a time. Either it becomes infinite but still closed, or if it is not, not closed, then at least we don't lose both points. So the interval is not going to be initially open; it will be half open. So the example of what I'm talking about is we already saw. That's what we started with. The area under the graph of the same function y equal 1 over x, and the area I'm talking about is this. The area that is unbounded, it continues on like this. Okay, and as you can see, the example is different from what we just saw in the sense that well, the region is bounded. The interval of integration, this one is bounded. Bounded, but not closed. So it's an interval, say, we could take 0, 1. I have to throw out 0 away. I have to throw out because the 1 over x is undefined at 0. So then our initial calculus 1 introduction into a definite interval does not apply because of that reason. It is simply undefined at that point, so we cannot carry out that computation. We cannot do Riemann sums. So, well, we know already how to handle it, but before that, you can tell me what the answer is. This is infinity, right? So we talked about that. I just mentioned it a minute ago. This is infinite. So this is infinite. Why is it infinite? Because of the symmetry of the situation with 1 over x. It is symmetric about what? It is, yes, but that's not what I'm talking about. It is symmetric about the diagonal. So then the two regions that we are looking at right now, the in green and the one that we looked at yesterday, are identical. So this one is from yesterday, right? And it is infinite. And then the region on the left is what we're talking about right now. And since we demonstrated that this is infinite region, infinite area, then it's going to be infinite as well, infinite area over here. So the region is infinite to begin with, or at least it's infinite in length. But it does not have to be infinite in area, but this one is. So, okay, so these are called, let me put it this way. So integrals, DEF stands for definition, integrals over intervals that aren't closed bounded, are called improper. So that's the only thing that makes these integrals improper is that it does not fit into the definition of the Riemann integral from calculus 1, which is supposed to be unclosed bounded interval. It's only improper until we figure out how to handle them, and we have a pretty good idea of how to deal with it, at least one of these classes. So let's list. So it continues on, this definition, looking at all of these possibilities. So I'll start with one that we did yesterday. So number one. So suppose f is defined on interval a infinity, and f is integrable on every integral a b larger than a. Okay, so just the way we did it yesterday. So we don't try to do the whole integral right away, but on every interval we know that the function is integral. So this integral, that's the only thing that I'm saying is that this integral makes sense. This integral makes sense. That's what integral means. The integral makes sense. This is a number. Okay, so that's what integral means. I'm not going to go back into the definition of the Riemann sum as the limit of Riemann integral as the limit of Riemann sums, but at the end of that computation, we end up with a number. Okay, so not infinity, so it's a limit, so it might not exist, but we assume that it's integrable, so which means literally that it does work, the limit exists, and the end result is a number. The difference is we do it separately for each b. A is fixed. Okay, so A is fixed as you can see, but B we allow it to be variable. So then we take the limit of this thing with B going to infinity, and that number, which might once again not exist, as always with limits, that gives me the improper integral from A to infinity. So, if limit exists. Every time you write a limit, you can also add this caveat about the possibility that the limit does not exist. If you want to be safe, then this is the way to do it. But it is presumed every time that as a possibility that the limit doesn't exist. And we already saw one example, not extremely bad, of 1OX. The limit does not exist in the sense that it is infinite, but it's not the worst case scenario, as a matter of fact, because it was actually informative, right? 1OX. This limit, let me just write it out. So as an example, integral from 1 to infinity, 1OX dx. Literally, we can write it this way, plus. Okay, so that's what we found yesterday. Okay, so it is informative because you cannot say it is indeterminate, for example, because it is determined. We have determined what it is. There is no ambiguity about it. It's limit that happens to be infinite. And so even though it does not a number, as we ideally would you would prefer, what was the last the computation for 1OX squared? I just want to copy this 1OX squared. The answer is 1OX squared is the answer is 1. Here you see, this is the computation that we did yesterday. So I could just write out that what we just discovered yesterday, integral from 1 to infinity, 1OX squared dx is equal to 1. Okay? So as you can see, just looking at the function, you cannot tell what's going to happen, but these are the two basic possibilities that infinite versus finite. So either it is originally still infinite, but it is infinite only in length and not in area. That's what the second one says, and the first one is both the length is infinite and the area is infinite. There is a third possibility. The third possibility when the limit does not exist in the literal sense. So it's not not even infinity. So limit that aren't even infinity. So remember any limits of this kind. Limit of a function at infinity which is not a number, nor it is infinity. So if we just go back to calculus 1 before we go deal with integrals, so let's just look at limits as we saw in calculus 1. What I'm talking about of a large-scale behavior of the function as we move along the x-axis on and on to the right, and see what's happening to y. It could be, if the limit exists, right, so say limit, say g of x is equal to c, x goes to infinity. How do we describe this? Plus infinity. A function g has a limit at infinity equal to c. What is it? There's a word for it. There's also a picture, very descriptive. What are we talking about? So you see what the limit means, that as x is growing larger, the function g, the output of the function g starts look more and more like. That's right. That's what we're saying here. So there is a straight line, y equals c, and it is the horizontal asymptote of the function of g. Okay, so the function g might approach it in some way which is not important at this time, but it is very nice behavior, and that's what we saw over here when the limit, some limit exists at infinity and is equal to a number. There is another possibility which is even more common. Say I take y equal x squared. Well, looking like this. What is its limit? Limit x squared, x goes to plus infinity. What is it? Infinity. Okay, so no horizontal asymptote. So that's then so this is number 1, this is number 2, and we saw these two examples. This is number 1, this is number 2. I'm not talking about the function itself, I'm talking about the integral. Remember, the integral is defined as a limit at infinity. Okay, so the possibilities of limits are so far number and infinity. What's the third possibility?
What?
Can you make it even worse than infinity?
0.
No, 0 is a number. It's a horizontal asymptote. It's bad, but yeah, it's just as bad as infinity. Yeah. Really nasty behaviors. Think about it. Oh, that's really bad. No, not that bad. What was the suggestion? There was something else. Undefined, yes. So this is kind of undefined, right? So infinity is the limit does not exist in the sense that, in a particular sense, that is infinite, but it could be worse than that.
A whole?
No, and at infinity there is always a hole. We cannot put anything there to finish off the job. There will always be something missing. It will be still infinity. It will be going to infinity along that slanted asymptote. Oscillation, right? So how about sine x? Sine x goes to infinity. What is the limit? the limit of sine x at infinity. The functions themselves, or the ones that I'm looking at, are nicely behaved, but the at infinity, the limit might not exist. So the description is simply say does not exist. And as I put it, it's not even infinity. So this is worse than infinity, because at least there's a pattern of behavior that you can compactly describe. So the function goes to infinity. That's what number 2 says. We're going to infinity. So and the area is infinite or something like that. Here it is in a more literal sense. The limit doesn't exist because we cannot say anything. The limit simply there is no pattern. There is no kind of behavior that we can describe in any way other than, well, we say it's oscillate, but then it could oscillate in a more nasty way and it still doesn't exist. So the third possibility is the whole thing doesn't exist, and this actual function provides us with example when our integration fails too, in a more profound way than simply being infinite. So what is the area? What is this area? So let's make one more step. So it's the same graph, but different function, different situation. Okay, same function, sine x, and I'm talking about this area, the area under the graph. So this area, what is this area equal to as we keep going?
Don't they cancel each other out?
It will, but sometimes it does, sometimes it doesn't. So if you don't have to guess, fortunately, we already know, we have the definition. So the area under the graph, y equal sine x from 0 to infinity, is always written the same way as an integral from 0 to infinity, sine x dx. By definition, we know what it is. We do not jump to and compute it. We go with the limit always. So you can see infinity there. So b goes to infinity. Integral from 0 to b sine x dx. So then these two things both from Calc 1. Computing integrals on a closed bound interval, we know how. Okay, calculus 1. We also know how to compute limits at infinity. That's also Calc 1. So here they come together. So that's the only challenge. Okay, so let's just do it one by one. It's not, we already did some of that, so we keep the limit intact for now. What's the integral?
Negative cosine x.
Yes, negative cosine x from 0 to b, which gives me what? Negative cosine b plus cosine 0. Okay, what is this limit equal to?
Something plus 1.
What is that something? Which is what? Well, once again, when in doubt, think dynamically. Imagine yourself walking along the x-axis and see what's happening to the function, and if you see any kind of pattern. It's the same problem as before. Is that this function we're looking at does have a horizontal asymptote. What? No. It's a cosine b. I mean, let's. I mean, it doesn't really matter. The name of the variable doesn't matter. Limit x goes to infinity. How about that? Negative cosine x plus 1. The name of the variable doesn't matter, so let's put x there. So we're trying to discover, we have a function, parentheses, and we're trying to discover whether or not it has a horizontal asymptote. Does it? Cosine x plus 1, does it have a horizontal asymptote?
Have 2.
No. What? No, cosine. It's, what's the graph of cosine? What's the difference between the graph of cosine and the graph of sine that we're looking at over there at the top?
Shift to the back.
shifted horizontally. Okay, so do you see the asymptote? This is what the asymptote is supposed to look like at the top. The graph is almost merging with the curve, with the straight line. It doesn't have to look as like this. It could actually behave. It could oscillate as long as this oscillation is dying out like this. But the end result, it kind of flattens out. So that's the meaning of the limit at infinity. The graph flattens out. If it is a number, then around that line, the graph flattens out. The sine function oscillates. The swing of the oscillation remains the same. It's still always between -1 and 1, right? So this one keeps going at the same exact swing between -1 and 1. So there is no pattern, there is no accumulation, there is no flattening of the graph. So there is no asymptote, there is no limit. And so what's the conclusion? So the limit doesn't exist. So how do we conclude this? That does not exist probably is just as well. We can say it does not exist. There is no area. There is no area not in the sense that the area is zero. It literally means that the area simply doesn't make sense. Okay, so the infinite area doesn't make sense. Okay, so it's not a number. It's not infinite either. It simply doesn't make sense. I mean, it happens sometimes. So it is to be expected. Every time you see a limit, there's a possibility that the limit doesn't exist, and whatever you're trying to determine or compute doesn't make sense. Just as much as infinity minus infinity might not make sense. Okay, so always keep in mind the fact that limits are bound not exist as often as they do. So let's take the other way, which we need to now have the opposite direction. So this is the definition right here. Okay, the first example or first instance of improper integral is integral from a to infinity. Now the corresponding one will be the same story, except it will be from on the infinity with minus infinity. Okay, so let's do that. So we have a definition. So we suppose once again in the same manner f is defined on negative infinity b fixed. And what we're trying to figure out is the limit from negative infinity to b, fx dx. So this is nothing but notation at this point. We have to explain what this is. We can certainly picture it. In fact, 1 over x probably would be just as good. So if I pick b equal to 1, this is the region where I'm talking about. This is the region. It is continues on to infinity. I'm trying to understand its area. I expressed symbolically in terms of this integral. Now we just need to explain what it is. What is it? How would you define such an integral following the idea from the previous definition? We cannot understand the whole thing simultaneously, but we need to look at the definition. This is what we did. We cut a piece of a bounded integral. We cut out that's what this integral is. We cut a bounded integral from the infinite integral and computed that integral first, and then took its limit. So the same story applies, except we're going to be expanding our interval not from left to right, as here, as you can see, b goes to plus infinity, but rather we'll be going to the left. So once again, trying to exhaust the interval. So our interval looks like this. Well, this is our interval, and we'll try to exhaust it like this. So we start with this, then we'll continue to a bigger one, but still from left to right, and then bigger interval, and then bigger interval like this. Expanding, expanding, expanding. So then this will be A. It will be integral still between a and b, but this time a is variable. The lower limit will be variable. So what do I write here? Integral from a to b, fx dx as before, and what's missing in front of it? Limit. Limit of what?
Is B, or A and B goes to negative infinity.
A goes to negative infinity. The lower limit goes to negative infinity. So let's see that picture. The green integral is from a to b. B is fixed, and we have to then move to negative infinity like this. Okay, and then at the limit, that limit might exist, might not exist, but that's the best we can do. That's how we find out. We have to, once again, in order for this to make sense, we have to impose an extra condition on f, just as we did. And so the condition is that f is integrable on every a infinity, a b interval, a less than b. Okay, then this definition makes sense. Okay, so there's really no challenge. We can very quickly carry out the operation that we were looking at, the computation for this function. So it will be integral from negative infinity to negative 1 over x dx. Okay, so it is equal to, according to the definition, limit with a going to negative infinity, integral from a to negative 1 over x dx. What is the answer, by the way, if you can guess right away? Is it infinite or not?
Yeah, it's infinite.
Yeah, it is infinite, because the answer should be probably, the whole computation is identical to the one that we did yesterday, except it will be all negative, right? So you can certainly can continue, and so 1 over x will be ln absolute value of x from a to negative 1, a goes to infinity, negative infinity, and, so it will be ln of, limit a goes to negative infinity, ln of negative 1 minus ln of a, and once again, the logarithm, as a goes to infinity, absolute value of a goes to positive infinity, and logarithm also goes to positive infinity. So this thing goes to positive infinity, so the whole thing is positive infinity, so the area is infinite. So all the ideas that we had yesterday also apply, so the powers have to be strong enough in order to make the strip to narrow down so fast that it will, so it's fast enough for the area to not to run away to infinity. Okay, so this one does. So even though it's narrowing down, every time we progress with a from right to left, the area increases less and less, slower and slower, but still fast enough so it still goes to infinity. Okay, but if you have 1 over x squared, it is narrowing down so fast that every time you add a little bit, it does not add up enough to have infinity at the end. Okay, so that still applies, and we're going to see that more. Well, now the only thing is missing is now the infinite interval, the one from the beginning to the end. So let me put it here. So what is the meaning of the integral from negative infinity to infinity? This one does not apply to 1 over x, because why doesn't this apply to 1 over x?
Because there's an asymptote at 0.
Because it's undefined at 0, that's right. So this one will not be applied, but it will apply to, say, the one that, remember this one? E negative x squared, so it's defined everywhere in this bell curve, going all the way to the left, all the way to the right. So how will you define it? One way is to simply go on with the similar computation to this. So you have two limits. The left limit go to negative infinity, right to positive infinity. It just does not work out as well as a much simpler idea. And this is the idea. You just cut it in half. That's all. So that's all there is. You can cut at any point. It doesn't matter at 0, at 1, at 2. The result will be the same. But as you can see, so the idea is we often do. We reduce the something new to something old. So we just understood. We were able to understood yesterday and today these integrals. They are infinite, but only in the infinity on one side. So then what do we do with half infinity on two sides? Well, we put these two together, and indeed that makes sense because we're talking about these two areas. So say this one, to the left of 1, it is infinite, but only on one side, and then there's the other one, infinite only on one side. Okay, so if you understand one, you understand the other. Okay, so as an example, how about we do this one? So I don't want to. This example, this is certainly is an important, very important bell curve. But let's take a simpler one. This one cannot be integrated anyway. So let's do something that we can handle. And then I'm talking about f of x equal to e negative absolute value of x, which is not a bell curve, even though it looks kind of similar. It will have a cusp here, like this. So it's like I take the absolute value function and just cut off the part that is to the right of the y-axis, and then make them 2, and that's what creates the cusp. Okay, so the function then is not differential, but it's still continuous and it's still integrable, so there is no trouble, and we can just compute it fairly easily. Let's do it in one line from the beginning to the end. So integral between negative infinity to positive infinity, e negative x dx, split it according to the definition to 2. 1 is integral. What did I do here? Okay, 1 is the integral from left to right, from negative infinity to 0, e negative absolute value of x dx, plus the second one taking care of the other one, from 0 to infinity, e negative absolute value of x dx. Okay. Now, before we go on and apply those definitions that we have, we simplify. How do I simplify the first one? We're integrating over negative values of x. So what happens with absolute value of a negative number? What?
They're going to be positive.
They will be positive. What should I write here?
You did a negative x.
No, it will be actually x. Negative because when x is negative, the value of absolute value of x is negative of x. So negative x. Okay. For negative, when x is negative, that's how we compute the absolute value. We just multiply the number by -1, and that's what it is. Okay, when x is positive, we don't have to do anything. So the second one looks. So this is x. The second one looks pretty much the same. E negative x dx. So as you can see, we want the exponent to be negative. And to the left of it is already negative, and the second one we have to have negative sign in order to make those positive x's negative. Okay, so so now we use the definition. Now we have two limits. One of them we will have already computed, but let's do it anyway. So this will be a limit with a going to negative infinity, integral ex dx, and this is integral, not integral, but rather limit. B goes to plus infinity, integral from 0 to b e negative x dx. Okay, so let me try to visualize these. So I'm talking about this one from a to 0, right? So I'm talking about this area, computing it first before taking the limit. And then on the right, so this is what I'm talking about, this one, this integral. Okay, and then not this integral, but rather the integral itself, not the limit. Okay, and then this one, where is that one? It goes from 0 to say b, maybe b here. A and b have nothing to do with each other. So we're carrying out these two computations, two integrals and two limits entirely separately. Okay, so let's do it. Okay, so we have limits. So computing integrals first before doing limits. So limit a goes to negative infinity. What's the integral of exponential function? E to the x from a to 0, and here I have a limit. We did it yesterday. What's the answer here? E negative x. What's the integral? Negative e negative x. That's right. From 0 to b. Okay. Substituting, we have e0 minus ea, and here we have a limit negative e negative b plus e0. Okay, of course e0 is 1, so that makes our life easier, but really we have to look at the ones that are actually variable. So now this one, we have to see where this one is going. Where is this going? A goes to negative infinity. Well, the graph of exponential function helps. It is, this is the part of the graph that we're talking about. A goes to negative infinity, and this is y equal e to the x. What's happening to y as we're going from left to right all the way? Is going to 0, right? So this goes to 0, and so does this one. Okay, so it's just the mirror image. And finally, what we have then, so e to the 0 plus e to the 0. Okay, so that area over here is equal to 2 from all the way to the left and to the right. Okay, so there will be there might be one problem like this on the homework, but there is more of improper integrals. Once again, what if it goes to infinity like this? We'll do it tomorrow then. Okay.